Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to focus a little bit more on the entropy of individual substances. So one of the reasons why we need to do this is if I'm going to try and determine an entropy of reaction, I need to have the entropy of my products and the reactants. So one of the starting places we can go to is actually what's called the third law of thermodynamics. Yes, I know we're skipping the second for now. But one of the reasons why this one is important is it says that a perfectly crystalline solid, so this would be, again, a solid with that perfect crystalline structure that we've seen earlier, will have an entropy of 0 if it has no temperature, so 0 degrees Kelvin. Because if it's perfectly crystalline, it means everybody is in a perfectly exact arrangement. Everyone knows their place. And if we are at 0 degrees Kelvin, it means I've got no kinetic or thermal movement. So at this point, again, it makes sense. There's only a single configuration the system can adapt. And at this point, then, well, my number of microstates is 1, and so my entropy is going to be 0 because the natural log of 1 is 0. And this is actually a really cool idea because now all I need to do is try and figure out how the entropy changes as I go from this 0 degrees Kelvin to whatever phase and temperature of the substance I care about. So we can go ahead and handle any of the temperature changes using our relationship of entropy and temperature. So as long as we know the heat capacity of all of the various phases, so this would be the solid, the liquid, and the gas, whichever ones it has to go through, and we know our initial and final temperatures, we can figure out how that entropy increases as I raise the temperature. However, it is worth noting that there is a very special subset of rules that handle temperatures less than 10 degrees Kelvin, because it turns out it's not so good to put 0 at the bottom of a ratio. However, accommodating for that, it turns out that we can go ahead and figure out how the temperature increases the rest of the way using this simple relationship. Then the only other things I have to worry about is what potential phase changes. So if I've got a solid, then all I need to do is figure out how the entropy increased with temperature. However, not all of our substances are solid. So I often will need to make use of my entropy of vaporizations and fusions. It is worth noting, as we've seen, these will always be positive values because the entropy will always increase as I go from liquid to gas and solid to liquid. It turns out, and we'll go ahead and talk about this later, you can actually figure out the entropy of vaporization from the enthalpy of vaporization, and the same thing with fusion. So we're going to go ahead and kind of skip this for now, but make note when we come back to it later. So if I know what my initial entropy is, and I know how the entropy increases with temperature, I can go ahead and go from that initial entropy to the entropy of the entropy of the solid at its melting point. Then I can go ahead and use the entropy of fusion to go ahead and figure out the entropy of the liquid at the melting point. Then I make use of my heat capacity to figure out the entropy of the liquid at the boiling point, use the entropy of vaporization to figure out the entropy of the vapor at the boiling point, and then again use heat capacity to figure out the entropy of the vapor at any given temperature. Now, for some substances like liquid water, I may just have care about some point here. However, if I'm looking at ice, also go here, and if I'm looking at water vapor, I have to go all the way here. So it is worth noting we can go ahead and stitch together all of these simple relationships to figure out the entropy of any substance at any temperature. So these entropies are commonly known as third law entropies, and you won't have to calculate them, have to spend too much time calculating them. However, I want you to be aware of these third law entropies because they're found in many various reference texts. So if I tell you to go ahead and find the entropy of blank substance, what the value you're actually looking up is these third law entropies, and somebody already did the hard work for you. That said, I also want to emphasize that when we found the enthalpy of a substance, we had no idea of knowing what the exact enthalpy is because we don't know exactly how energy is split up in an atom or a molecule. The same is not true of entropies. You can't actually determine the exact entropy of a substance under any set of conditions. And that's exactly what these third law entropies are. So now we have an idea of how to find the entropy of a various substance, and we know how to find the entropy of a reaction. Together, we're going to take these ideas and pair them with enthalpy to figure out exactly how favorable a reaction might be and when it might occur. Next time, we're going to finally talk about spontaneity. Until then, take care.